This movie is about the basics of power inverter technologies. This is a technology which is used today in millions of applications to convert a DC voltage to an AC voltage. The applications are, for example, in electric trains, electric buses, or in e-cars, and many, many millions of other applications. This movie is really about the basics. The core element of power electronics is a switch. This is an example of a circuit. This is the most primitive power electronic circuit you can have. You even can operate it manually. So here you have a battery. This is a DC voltage source. In this case it would be 1000 volts. And here you have a load. It could be a motor or anything else. You have a reactive and an ohmic load. And here you have the manual switch, and you can see that if you open and close the switch, you connect or disconnect the source to the load. And by doing so, you get the voltage switch from 0 to 1000 volts. Of course, if you do that manually, you are very slow. And what you also would like to achieve is that you do not only switch from 0 volt to plus 1000, you would like to switch from minus 1000 to plus 1000. But then you need a little bit more switches, 4 switches to be precise. In order to control 4 switches manually, it is quite difficult. And therefore, you would like to control these switches electronically. So you need somehow to connect a kind of an electronics to the switch. So here you have now, instead of a hand control switch, you have now a switch which can be remotely controlled by means of an electronics. So this is the piece of electronic you could then set up. But still, this electronics can be controlled manually, but it can be remote controlled. So that the first step would be to develop a manually controlled, remote controlled switch. This would operate as follows. You see, it's still like before. You can open and close the switch. You see how the voltage is jumping from plus to minus, but it is remote controlled. It is not anymore at the switch itself. It is remote controlled. Since we have now an electronics, we can remote control not only one switch, but 4 switches at once with a very simple control logic. So we still have a push button, but we can now have a control logic where we can remote control 4 switches at the same time. This is how it looks like. So still we can remote control the switches, but it's not only one switch as before, we have now 4 of them. And it's always so that these 2 switches have to be basically on at the same time, whereas these ones are off at the same times, or vice versa. These ones are on and these 2 are off. They can never be closed at the same time, otherwise you would have a short circuit. So let's now show this one. You can now see that the voltage at the load is not jumping only between 0 and plus, it is jumping between plus and minus. So this is already a big step. But if you want to do so manually, you see it's much too slow. You want to be much, much faster. Therefore, you need to have an electronics which automatically controls these switches. So the next step is now that we automate the simple control. So moving from manual control to automated control. I have now replaced my lovely push button by a sinus signal generator. And let's see what happens now. You can now see that the output signal is a rectangular signal. It is according to the 50 Hertz signal generator here. So it goes up and down. At least now it's automated. I can change a little bit the time resolution that you see better what is going on. So this is now basically 50 Hertz. It is very rough. In reality, it would create a lot of losses. That's what we do not like. So we would prefer to have a sinus-shaped output waveform. And let's see if we can achieve this. The trick is that instead of putting one of the signals of the comparator to ground, instead we put it on a pulse code modulator, PCM. This is the one of the core technologies in power electronics. Here you can now see the principle of a pulse code modulator. So instead of having the signal grounded as it was before, I have the reference sinus signal as before, but now I have basically a triangular reference signal put in parallel. I compare these two signals. Let's see how this looks like. I have now this triangular signal you can see here, and I have this other sinusoidal reference signal, and if you are looking at the output, we see then this pulse code modulated signal. You can see that basically the higher the voltage, the broader the pulse width is. If I have a negative voltage, in this case, the pulse width is basically 0. So this is what we will need now to control our inverter. Now we put it all together and let's see how this works. So instead of connecting one connector of the comparator to ground as before, I have connected them to this triangular signal generator, so the sinus and the triangle work in parallel as before, as I have demonstrated it on the PCM technology. How does it look like now? Let's run it. And you see now the output signal at the load is already a little bit better than before, but still pretty rough. So this would still generate a lot of losses. But what we can now easily do is increase the frequency of this triangular signal. Let's do so. So instead of having 1000 Hertz, I go to 10,000 Hertz. And now the signal will look already much, much better. It may not yet be good enough. So we can even further increase the sampling rate of my calculator. And you see now that the signal is already close to perfect. So this is now the final shape of my signal, and you see it's close to perfect. So you can even further increase the sampling rate of the calculator. You can further increase the frequency of the signal generator. And basically today you go up not only to 1000 or 10,000 Hertz, you go up above 20,000 Hertz, so there is no audible noise anymore at all. Thank you.